Okay, this is a screencast on Kirchhoff laws. We're going to cover Kirchhoff's first law and Kirchhoff's second law. The first law is relating to junctions, current at a junction. So we're going to set up a simple junction like this. We have a current leading towards the junction of 1 amp and a second current value of 1.5 amps leading towards the junction. So we should know that because of this, a current of 2.5 amps will leave the junction. So we can say that I1 plus I2 equals to I3, and we should be familiar with this concept already. We can rearrange this formula to say, therefore, I1 plus I2 minus I3 equals to 0. Why do we make I3 negative? Well, basically, when dealing with Kirchhoff's first law, any current values leading towards a junction are assigned a positive value, and any current values leading away from a junction are assigned a negative value. So when we add up the current values for a junction, we just have to keep that in mind. So we can rewrite this as the sum of the currents equals to 0, and this is for a junction. That's Kirchhoff's first law, so we put that in a box. Kirchhoff's second law deals with things called loops. A loop contains all the components of a circuit. One full loop being from one side of the battery through whatever components are in the circuit in a loop around to the other side of the battery. So if we set up a simple circuit, we're going to start off with a power source, a cell, and then we're going to join that to one resistor, a second resistor, and a third resistor, and then back around to the other side of the battery. And we're going to assign those resistance values R1, R2, and R3. And we're going to assign an EMF to the battery. EMF, electromotive force, is just another way of saying voltage, really. It's the thing that gives the charge the push to move through the circuit. Electromotive force, the force that drives the electrons through the circuit. Now, it's basically interchangeable with the word voltage, except that sometimes when we're talking about the voltage, we could be talking about the voltage drop across a resistor. So when we think about the voltage across a resistor, or the voltage drop across a resistor, we're talking about a loss in voltage. It'll take a certain amount of this 9 volts to move a charge through R1. So the EMF, we use epsilon for electromotive force, drives the charge through the circuit, and then any resistor or component in the circuit will use up some of that voltage, so that voltage will be subtracted from the total EMF of the battery. So in this case, we're just going to say that all the resistors have an equal value, so the EMF or the voltage is going to be split evenly across the 3. So we're going to give them voltage values. So the voltage drop across R1 is V1 and so on. Now, because they're equal value resistors, like I said before, the EMF will be divided equally across them. So there'll be a voltage drop of 3 volts across R1, another 3 volts across R2, and another 3 volts across R3. So we can say that the EMF of the loop is equal to the 3 voltages, V1 plus V2 plus V3. Or another way to say this would be that the EMF minus V1 minus V2 minus V3 all equals to 0. So in other words, if you've got an EMF of 9 volts, minus 3 volts for the first resistor, minus 3 volts for the second resistor, and minus 3 volts for the last resistor, that all equals to 0. You've used up the full 9 volts from the battery or the cell. So we can say the sum of the voltages equals to 0 for a loop. And this is Kirchhoff's second law, so we put that in a box. So we use these two laws to solve a circuit. I'll explain what I mean by that in a second. So just to write down our 2 laws that we're going to use in this example, and then I'm going to set up a circuit. Now you'll notice in this circuit we've got 2 batteries, or 2 cells rather. So there's going to be an EMF from this cell and an EMF from this cell, and then we've got a couple of resistors. So we're going to assign some values to these. We're going to say that this is EMF 1, and over here we have EMF 2. I'm going to assign resistance values R1, R2, R3, and R4. And then I'm going to assign voltage values across those resistors. So the voltage dropped across each resistor. Voltage drop across R1 is V1, voltage drop across R2 is V2, and so on. Now the last thing I need to do is to assign current values, and I have to sort of try and figure out the direction that the current is going to move through the circuit. And that really depends on these two EMF sources. So this battery is going to drive the current in this direction. Remember, it always goes from positive to negative. But what's going to happen down here, because we've got a second cell producing an EMF, and the current from this cell wants to go from positive to negative as well, so it wants to go this way. And the direction that the current takes will depend on the relationship between the two sources of electromotive force. Which one's essentially stronger will determine which way the electrons or the charges actually go. But the fact is, to solve the circuit, we don't actually need to know the direction that the current goes. We can make a sort of a guess or an estimation. And the equations will take care of that for us later on, and I'll explain what I mean by that. So I'm going to assign some sort of what I think the direction that the current is going to travel through this circuit. So I'm going to place in what I'm going to call I1 here before we get to the junction, and then we're going to have some other current moving through this part of this circuit. This is a branch which connects two parts of the circuit together. So I'm going to call this I2. We're going to have some other current value over here, I3, and I1 is going to return over here and return back to the other side of the cell here. If we have a current I1 leaving the battery on this side, then we must have the same current I1 returning to the other side of the battery or the cell on this side. So we're going to use a sample question, and we're going to give a value of 12 volts for our first EMF, a value of 6 volts for our second EMF, and then I'm going to say that each of the resistors have a value of 2 ohms each. So now we want to solve the circuit. If you're asked to solve the circuit, that means that you have to find all the voltage and all the current values through each component, each part of the circuit. So we're going to use Kirchhoffs laws to do that. And the first thing we're going to do is we're going to write down Kirchhoffs' first law as it is associated with this circuit. So if we add up all the currents at this junction here, for example, then we can see that there's a current value of I1 approaching the junction. Remember I said if it's approaching the junction, it's positive. You also have another current value entering the junction from this side, which is I3, and you have a current value leaving the junction here, which is I2. So if I add up all of the current values, I get I1 minus I2 plus I3 equals to 0. And I'm going to call that equation 1. Now I'm going to think about the voltages in a particular loop of the circuit. So what do I mean when I say loop? Well, we have a loop here, going through the circuit and back around to one side, and we have another loop over here. Okay, now we can choose to go through the loop in whatever direction we want. The direction that we decide to go through the loop when we add up the voltage values associated with Kirchhoff's second law doesn't matter. We can go clockwise through the loop like this, or we can go counterclockwise through the loop. Okay, but depending on which way we do that, the EMFs and voltage values are either going to be positive or negative. So we have to obey a certain rule for when we're doing that. Now I'm predicting that the current is traveling in this direction through the loop, so I'm going to choose to move through my loop in that same direction, in a clockwise direction. If you move through the loop, and with Kirchhoff's second law, what we're really doing is adding up all the voltages and EMFs, remember? So for each loop, we're adding up all the voltages and EMFs in the loop. If we move through it in a clockwise direction, in the same direction as the current, then the voltage across any resistor in the loop is going to be assigned a negative value. Why is that? Well, if you think about what this EMF over here is doing, this voltage from the cell, is it's pushing a charge through this resistor. And we already said that the voltage across this resistor is what we call a voltage drop. It's a reduction in the amount of energy available to the charge. Okay? Or in other words, some of the voltage is being used up in moving the charge through this resistor. So if we're moving in the same direction that the current moves through the resistor, then the voltage value for that resistor is going to be assigned a negative value. If we move the other way, it would be positive. Okay? Now, when we're moving through the loop, we have to consider our EMF values. Are they going to be positive or negative? Well, as you move through the loop and you add up the different components in the loop, if you move from the negative side of the cell through to the positive side, so from negative to positive, then your EMF value is positive. If you're moving through the loop from the positive side of the cell, as we are here, to the negative side, so from positive to negative, then the EMF is assigned a negative value. And that makes sense. If this EMF is positive, remember the positive side of the battery is the side that the current wants to come from. We go from positive to negative in a circuit. So if this is a positive EMF and wants to move the circuit in this direction, and this EMF down here wants to move the current in this direction, then if this is positive, this is going to have to be negative, right? Because they're sort of opposing the direction that they want to send the charge. Okay, so I'm going to use the second law, and I'm going to start just by considering the EMFs. So I have a positive EMF 1 and a negative EMF 2. So I have epsilon 1 minus epsilon 2. And then I'm going to move through the loop and add up my voltage values. And because I'm moving clockwise through the loop in the same direction as the current, the voltage values are going to be negative because it's a voltage drop. So I'm going to get minus V1 minus V2 minus V4 is equal to 0. And I'm going to call that equation 2. Now if I do the same thing for this loop over here, and again it depends on the direction that I choose to go through the loop, but generally I try to go through the loop in whatever direction the current is going, because that just makes it easier for me. So if I do that, then this EMF value is going to be negative for this loop as well. So when I add up the EMFs and voltages for this circuit, I'm going to say and, also using Kirchoff's second law for the second loop, I have a negative EMF 2 minus V3 minus V4 is equal to 0. I'm going to call that equation 3. Now at this point I'm going to use Ohm's law, V is equal to I times R, to get rid of these voltage values and start assigning current values. I want equations using current rather than voltage for this purpose. So the first thing I'm going to do here is I'm going to get rid of my epsilon 1 and epsilon 2. I'm working with equation 2 right now. So we already have from the question that epsilon 1 is 12 and epsilon 2 is 6. So I assign those values. And then I'm going to say minus, but instead of V1, if I look, where's V1? It's down here. From V is equal to I times R, I can say V1 is equal to I1 times R1. Okay? I don't know what I1 is, but I know that R1 is 2, because that's the value that it was assigned in the question. So I can say, instead of saying V1, I can say 2, which is my R value, times I1. And then I can do that for my other voltage values as well, and I get the following. So I've just substituted my voltage values in equation 2 using Ohm's law. And if I do that for my other equation, equation 3, then I get the following. Why is it useful to do that? Well, now I've got 3 equations in I. So 3 equations involving current. I've got 3 unknown currents, but because I have 3 equations, I can simultaneously equate them to figure out those current values. So from equation 1, I can say that I3 is equal to I2 minus I1. So I'm going to work with I3 first. I rearrange that to get I3 by itself. And from equation 2, if I summarize equation 2, add the different voltages together, add the currents together, then I get 4I1 plus 2I2 equals to 6, and if I simplify that, I get 2I1 plus I2 equals to 3. And if I do the same thing for equation 3, looking at equation 3 over here, if I move this 6 over to the other side, then I'm going to get minus 2I3 minus 2I2 equals to 6, and if I simplify that, I get minus I3 minus I2 equals to 3. Now, from earlier on, I have a value for I3 in terms of I2 and I1. So I'm going to substitute equation 1 into equation 3 to get rid of that I3 value. So I get minus, subbing in for I3 is I2 minus I1, all that minus I2 equals to 3. And if I simplify that, I get minus I2 plus I1 equals to 3. And therefore, if I get I1 by itself, I get I1 is equal to 2I2 plus 3. Now I'm going to sub this into equation 2. So I'm going to substitute for I1 in equation 2. And if I do that, I get 2 times, instead of I1, I get 2I2 plus 3 plus I2 all equals to 3. And that allows me to work out I2. So now I have an equation with one variable. I get I2 is equal to minus 0.6 amps. That minus is very important. I'm going to discuss that in a second. But if I sub that I2 value, first of all, into equation 2, that's going to let me solve for I1. So I get that I1 is equal to 1.8 amps. Subbing I1 and I2 into equation 1 gives me my last variable, I3. So I get that I3 equals to minus 2.4 amps. Now, I1 is positive, that's fine, but I2 and I3 are both negative. I said earlier on that it doesn't matter over here what direction we sort of define this current moving through either of these loops. We can kind of guess because the equations will sort it out for us. And this is what I mean by that. If your current values end up being negative, like they are here and like they are here, that means that you chose the wrong direction. Okay, so you need to change the direction of I2 and I3. So we're going to do that. So I2, I have it going in this direction over here. I'm going to change that. So I'm going to say I2 and I3 should be in the opposite direction. So let me change that. I'll get rid of this little directional arrow and I'll replace it with an arrow pointing in the right direction. And I'm going to do the same thing for I3 over here. Get rid of that arrow and replace it with an arrow going in the correct direction. So this is the actual direction that the current moves through each part of the circuit. So now I've got my current values and I can use those to find my voltage values. So I can simply just use V is equal to IR for each resistor. If I'm working over here with R2, for example, V2 is equal to I2 times R2. I now know I2 and I knew R2 from the beginning. R2 was just 2 ohms. So I can solve for V2. So I'm going to do that for each of them. So I find that V1 is equal to, well, it's going to be equal to I1 times R1. I have from down here that I1 is equal to 1.8 amps. So I substitute that in for I1 and R1 is just 2. So I get that V1 is equal to 3.6 volts. Similarly for V2, I find that it's also 3.6 volts. V3 is 4.8 volts and V4 is 1.2 volts. Now I've figured out all my current and voltage values. So the last thing that I should do is I should just use Kirchoffs laws to check that the I and V values are correct. So if I come over here and I use the first law, which is that the sum of all currents at a junction should equal to 0, if I add in, well, I1 is going to be positive, I2 is going to be positive because it's coming towards the junction, and I3 is going to be negative because it's leaving the junction. If I get the sum of those current values, well, I1 up here, that's going to be equal to 1.8 amps, right, from down here. I2, that's going to equal to 0.6 amps. And if you're saying, well, hang on, he said that I2 is equal to minus 0.6 amps over here. But remember, the minus just told me that I was going in the wrong direction. And I accounted for that when I changed the direction up here. So when we get our current values, we're interested in the magnitude of the current. The positive or negative sign tells us whether our direction was correct or not. So this is current heading towards the junction, so it has to be positive, right? And my final current value, I3, is going to be 2.4 amps. Same thing again. I said it was negative down here, but I accounted for that when I changed this direction here. So using Kirchoffs law, if I add up the currents going towards the junction, well, I1 and I2 are both heading towards the junction, so 1.8 plus 0.6 gives me 2.4. And if I subtract my I3 value, which is leading away from the junction, minus 2.4, that gives me 0. So that satisfies Kirchoffs' first law. And if I do the same thing for the voltage values in a loop, I should find that that's also correct. So that's just a way of checking your work and making sure that your voltage and current values are correct. So this is the circuit solved using Kirchhoff's laws.